Welcome to Brothers of the Serpent podcast.
And welcome back, ladies and gentlemen, boys and girls, aliens, demons, monsters, and serpents, skirptards, and everyone else. It is Brothers of the Serpent podcast. We are coming to you live from the, well, not really live, from the 10 by 10 by 10 tangent cube of science. We have a guest with us today, the engineer, GMA, Archer Finley. He is the expert.
He is expert. Ask him a question, he is expert.
One of the original SnakeBros here with us today. So, this is episode 15?
Yeah.
Yeah. Wow.
We've come a long way
Wow.
from episode 2.
So I think we're probably going to be digging into GMA's mind today on all things electrical
Now, we just brought him in here just so he could just sit there.
and make fun of us.
Comment.
No, but yeah, we were wanting to talk about electricity. And
We had
Just
the three of us had a conversation years ago about this, and I would like to kind of recreate some of that.
yeah. I remember I had just found out that nobody really knew like how it worked, and I guess that's like what we talked about last time, in that there's a law that tells you what happens, but the theory, no one is really sure like as to what it is. There's multiple theories of what's going on, but we don't really know.
Yeah. So
what
give
is.
us a rundown, GMA. Give us the basics.
Well, I mean, you're kind of right in that. Like we understand the underlying reaction or the effects, but we don't understand the cause. So it's kind of like gravity in that we like y'all said in episode 13, where we understand that there's a relation to the mass of the planet and the radius of the planet and how
Right.
far away from the planet you are. It's kind of the same thing where we understand that there's relationships between particles that cause what we call electrical forces, but we don't understand, from my understanding, we don't know the underlying cause for those forces.
So there's
Right.
no explanation for the mechanism.
Yeah, like they say that with magnets, the actual, when you're looking at a diagram of magnetic field lines, they're saying that those magnetic field lines, photons are
Right.
flowing along those magnetic field lines, but where are those photons coming from? What,
Yeah. What's generating them and why are they doing that?
Yeah.
Yeah.
What causes that?
Yeah. So DC and AC, like a DC power source is basically what? How does that, like, what are the
So
differences?
basically, a DC power source. Let's go back and just start about potential. So
Yeah.
potential, it's like with gravity again, where potential energy is, say you lift up something like a baseball, it has potential energy
Okay.
because there's a differential based on the gravitational field.
Right.
So
The potential
When you-
is like it could fall to the ground.
yes,
Okay.
and so there's a gradient, a gravity gradient, basically, that's causing a difference in potential between the 2 points that
Okay,
would cause
yeah.
the ball to fall. Same basic idea with electricity is that you have an area with, so let's just go with the standard model for now. You have an area that has a lot of electrons versus an area that doesn't have a lot of electrons.
Okay.
So the area with a lot of electrons is the negative
Right.
side, negatively charged side. And the area with a lack of electrons is the positively charged side.
Right. And so they'll want to flow from one to the other to equalize? Is that the idea? And
Yes,
That's,
yeah,
that's what
that's
creates
the potential.
Okay.
That's the potential. So it's like holding a baseball up.
Okay. And
so
then-
removing electrons is creating that holding the baseball up.
Okay,
basically.
right. Okay. And then AC is like a
AC is the same thing. You still have a potential. It's just that it's moving back and forth instead of in one direction. So think of a river. DC, it's always moving downhill one direction.
Okay.
Whereas AC, the water's never going anywhere. It's just going back and forth.
So
Okay,
it's like a
So
resonance.
It's a
resonance. Yeah. Well, it's not necessarily resonance. You have resonant frequencies within there, but it's a literal moving back and forth of the electrons. Instead of the electrons flowing in one direction because there's a constant potential,
Yeah.
the potential is moving. It's
being
reversing polarity every cycle.
Right.
So how does that
So-
that work with, like, so if you have electrons in this one side and fewer electrons in the other side, and you verse polarity, do they instantaneously switch sides? So there is a flow in the moment that you reverse polarity?
and that's when you start looking at like solid state electronics and the underlying mechanisms behind that. There's actually electron flow. So there's a velocity. And that's I believe a factor of the probability that the electron will hit another subatomic particle within the medium it's traveling through.
Okay.
And so that affects how fast it can move through the medium.
So
Right,
there's like a resistance in the...
Yeah, but
medium.
we want to be careful using the term resistance.
Right. This is by the way, like I was listening to 13 again, and like I was saying on there isn't a discernible flow, and there is. Like I shouldn't have said that. There is a discernible flow in any circuit. Like if you have something, if you have one component here and then another component after that in the circuit, like the first component will change the field before it gets to the second one. So there, I mean, even if you can't tell because it's going light speed or whatever, there is a flow direction. And I was saying that there
Yes,
isn't a
there
flow.
is a
Yeah,
flow direction,
right.
yes.
That was just completely wrong. I was dumb for saying that.
But going back to AC, the flow direction is back and forth instead of constantly in one direction.
So what happens when you put a device in the circuit that begins to convert the electrical energy into some other form? So like, let's say heat and light.
Okay.
What
so
happens
let's
to
start
the...
with the easiest thing. So let's say a power resistor, that basically electricity is being turned into heat and
Okay.
dissipated off as heat.
Right.
So you basically have a piece of material that the electricity is running through that is dense for the electrons to go through. So as they move through, they're colliding with, as far as I understand, as they're moving through, they're colliding with the particles inside that
Right.
piece of material
And exciting them.
slowing down
Yeah.
and transferring energy into that material.
Okay.
So when it's an AC circuit and you're doing this reversing of polarity, it's the reversing motion of the polarity in that resistor that's caught. That's because
No,
we were talking about a
it'll
river
happen
flow.
with AC or DC. The heating
Right.
up will happen either way.
That's what I was trying to figure out. How does it work with AC if you don't actually have a constant direction of flow?
Because the particles are still moving.
They're still having to go back and
They're
forth
going
and
back
oscillate.
and forth, yeah.
'Cause AC is-
because the potential is basically shooting them through one way and then shooting them back through the other way.
Right.
So you're still having
Like a saw
electrons moving
action.
through. Yeah.
Yeah. It's
Okay.
still
Saw
running
action.
and
Yeah,
it's-
that's what I was wondering.
It's only
Yeah.
60 cycles a second, so that's
Well, in the U.S. it is.
right. Okay, but yeah, well, how even it's not 186,000 cycles a second, so it's
No,
they
no.
can move pretty far.
Yeah, they can move. And I was thinking about that not too long ago, in that there is a limit to the amount of power that you would be able to deliver based on the frequency.
Right.
So the slower the frequency is, the more, think of it like a water again, the more water you're moving through
Okay.
versus when you're at a very high frequency, it's
just a tiny little bit.
barely
Yeah.
moving. So you're not transferring as much actual power at higher frequencies.
But can it be considered? This is what I've
Or
always
you
wanted to
can't
ask.
transfer as much
Right.
power at higher frequencies.
Can it be considered a kind of a mechanical force because it's a vibration? It seems like it's like a ringing almost.
So
Because okay, this is the thing. So if you got this miles and miles of copper wire,
Mm-hmm.
and I start and I plug it into a system that's doing AC.
Yeah, back
it
and forth.
basically nothing. I mean, like, what is it pushing?
So think of it like a tube of water where it's an incompressible fluid.
And it's already full of water.
It's already full of water.
Right.
So when you push on one end, it moves out, and
Right.
vice versa.
Okay, so
So-
and that's why.
So if you vibrate one end, the whole
The
thing
whole
begins
thing
to
is
vibrate.
vibrating. with
And then
it.
you can convert
Yeah.
that sort of reciprocation or whatever to energy.
Yes.
In some other form.
Well, and typically, like in the case of an electric motor, we use the interaction with magnets because the electrical force can move the magnet and vice versa.
Right.
Right, and that's always like angular somehow, right?
Yeah, so that follows the right-hand rule just with most anything in physics. If you make a thumbs up sign,
Yeah.
if your thumb is going in the direction of the electrical current, then the magnetic field is rotating the direction of your fingers. And
Very interesting.
Vice versa, if your magnetic field is going in this direction, your electrical current is being generated
Right.
in this direction.
Yeah.
So
And
That's cool.
okay, so I was just listening to something that was talking about angular momentum and saying that was one of the most mysterious things in physics. That it isn't really understood why something that is rotating has a momentum along an axis.
well, I mean that goes back to inertia. Why is inertia?
Right.
Why is momentum?
Yeah.
Why do things that are moving want to
But
keep
it-
moving? Why do things that are
Right,
stopped
but
wanna keep
it's easier to see, like, if I've
Yeah,
got the
stop.
baseball and I'm in space and I throw the baseball, it has momentum along the vector which I threw it, and it's moving along that vector. But something that's just spinning, why does it have momentum along its axis, even though it's not going in that direction?
Well, my reasoning is that you still have mass rotating around that axis.
Right.
So that mass is what's creating the momentum. Or-
Yeah, I agree. I just think it's
Yeah.
fascinating that, and then it's only in this one direction.
The momentum is perpendicular to the
Right.
Yeah.
It's-
to the motion.
Yeah, it's weird.
It is weird.
But maybe that's more the what y'all were talking about episode 13 with the
Elastic universe.
more the irrational number.
Oh, yeah.
Part of it, like maybe that's part of the irrational part of it.
Okay, yeah. So, go. Oh, you have something to say?
Yeah.
Okay, I've been thinking more about this. I was doing some work the other day and thinking about this, and like, it occurred to me that quantum superposition. I'm jumping way off. What?
No, it's fine. We'll detangentize.
Yeah, it's taking a brief tangent here, but quantum superposition. Like, I was thinking that is this. Okay, I've got to figure out how to describe this. When something is doing something and also not doing it, that's quantum superposition, right? So you're looking at some quantum object and it's both vibrating and not vibrating, or it's both rotating and not rotating, right? And considering the idea that like some of these properties are coming from some other world that is like running perpendicular to ours in terms of the warp and the woof, right? So a quantum superposition is actually us seeing some object as it sits both in our universe and the other. In other words, we're looking at an intersection of the threads. We're looking right at the intersection, and so it appears to be doing something this way and something this way that are mutually contradictory. You can't do both of them, but
Yeah.
because we're looking at this intersection of the universes, or whatever you call it, the worlds, we see it as being both.
Yeah. Well,
Briefly, and then what that led me to think of the uncertainty principle in that, or even the double slit experiment where the collapsing the wave function, right? Where if I choose to like try to get the velocity of something, or the velocity, I cannot give you the location. Or in the double slit experiment, it's a wave until I look at one of the slits, and then suddenly it
And then
starts to be a
suddenly
particle.
it's there, yeah.
And I was thinking about this ancient idea of these two different worlds and how one is perfect knowledge and the other one is perfect ability to act. And it occurred to me that, like, could it be that the reason that happens that way is because my action of choosing to get the velocity as opposed to the location, or choosing to look at this slot versus that one, is actually then like making the choice. Like the other universe can't make the choice because it cannot act, right? And so it's doing both until I do an action of choosing which one I want, and then the other one becomes completely out of reach, right? You see what I'm saying?
the other option goes the other.
Goes into the other universe.
Yeah.
Right.
That's cool.
That's mind blowing.
So in quantum superposition, the same thing. Like, we're looking at it being both ways.
Well, and part of that is like the superposition state is before we've looked at it,
Right.
before we've observed it. So
Yeah.
once we've observed one or the other,
Right, and then it becomes it becomes one or the other.
Binarizes to one or the other, but
right. And
until
it just,
then,
yeah, it was just fascinating to me that I suddenly thought like, okay, so it's our action that picks one or the other, that sets the property of that thing. I don't know. I don't know where to go with it from there, but that just like, I thought that was really badass.
That's cool.
Okay. So, again, I want to go back to the AC. Like, I keep thinking of it as being, like Kyle said, a resonance.
well, it's not really a resonance. It's like I said before. It's so you have think of it. I'll just try to make an example. You have a generator at the plant or at the power facility,
Right.
Like whatever turbine that's being turned by water or steam, or it's sitting there turning, and the magnets are basically pushing and pulling electrons in those wires.
Okay.
And so at your house, at the other end, you're getting that push-pull because
Right.
it's an incompressible fluid, basically.
Okay. So you mean it's not a resonance because something is causing this?
Yes,
Okay.
yes. So it's not a secondary.
It's not a
effect.
resonance like
Hitting a
the
bell and it
oil
rings.
moving through a hydraulic system is not a resonance.
Exactly.
Yeah.
It's a direct cause
I see.
or direct effect of a cause instead of a resonance.
It's sort
at
of
least by
and if
my
you hit it,
thought
it would
is
ring.
you get the harmonics. Like in a
Right.
60 hertz system, you have a 120 hertz resonance and a 240 hertz
Right.
resonance and all that.
Right. So you can get a resonance out of
You
it.
can get resonance out of it, but it's
the initial thing is not
the
a
initial
resonance,
thing
yeah.
is not a resonance. It's a actual push pull.
I wonder if it. Okay. So, and we generally use copper or aluminum wires, right? Surely those
Yeah,
have a
yeah.
resonating frequency. Could we take advantage of that by making the AC system work at one of those
Oh,
frequencies?
that's a great idea.
Now, so that gets into, I think, if when you're looking at that, you have to think also about, like in filter design, you have underdamped, damped, and underdamped, and overdamped, and I can't remember what the third one is. It's like balanced or something like that.
in
But,
filter design.
basically, when when you get a sine wave in, it'll either decrease the amplitude of the sine wave, allow it to continue at the same amplitude, or
Make it go-
increase it until it blows up,
Okay.
basically, or
Yeah.
rails the system.
Right.
And so, if you could tune the lines and your frequency so that you're at not an overdamped or an underdamped, but
Right. It's steady.
a steady,
a stable. Yeah.
But
system.
but I'm saying.
But if you got to an overdamped or an underdamped situation where it starts
Yeah, yeah.
blowing up and you're just
Right, so you would
blowing
have
up
to
your
have you'd have to have something to where like you would begin the resonance, and then you would have to like pull way back on the power you're putting in because it's ringing after that. You don't want to keep increasing.
Yeah. Basically, you're just barely pushing the swing at
But
that
that's
point.
the advantage. That's
Yeah,
that's what I
yeah,
mean. Like,
yeah,
that's the
yeah,
advantage. Like once
yeah.
you get it going,
I could see it totally being possible.
yeah,
absolutely.
that would be sweet.
Because then you're not sitting there pushing the swing every time. You're just barely tapping.
Right,
to
you're just
keep it
tapping it,
going.
letting it keep going, and
Yeah.
you can still pull power out of it.
Yeah. See, the problem with that though is that because you have different power lengths of power lines and different
Right.
factors changing resistance and capacitance, because there's also capacitance between the power line and the ground you have to take into account, and inductance of the power line as well. So you actually have resistance, capacitance, and inductance all creating a giant filter circuit. And so because there's all these variances across the world and across the country in power grids, you'd have different frequencies all over the place.
So there wouldn't.
But so
So-
the Tesla coil, right? We had talked about this before. It's basically a transformer.
Yeah. And it's, sorry, go ahead.
He has like one very large short wire, very fat short wire, and then an extremely long fine wire
The secondary, yeah.
that's wrapped. And what he did was he tuned based on the frequency of alternation, the alternation of the currents. He would tune the big fat wire, like keep moving, say
The tap on it.
right
Yeah.
where it was along the wire, say shortening that circuit or lengthening it until it became in tune with the finer wire, and that system in his lab became harmonically tuned.
Yeah.
And then the power generation from that transformation was extremely great. And then you could move it out from there without worrying about how long the wires are going somewhere and all that kind of shit. Because you use it, you use that resonance within
that transmitting system.
A system that you can determine the sizes with, you know what I'm saying? And then once you get the benefits from it, then you send it out.
So the Tesla coil acted like an amplifier of some kind? Or
it did.
Like a horn?
Yeah. It was normally like a normal, basically a normal transformer on a large scale, right? And he would tune the easy side of it, which the big wire only had it was like 2 turns.
Right.
The small wire had 10,000 turns.
Yeah.
Right.
Going all the way up that pole in the middle.
So he could calculate, say, the mass or whatever of the small wire, and then try to get some idea of how big to make the big wire.
Well, there's actually a ratio of the wire diameter and the number of turns.
Okay, that's right. He has an equation for that in some of his patents.
Yeah, it's like wire diameter over number of turns for one side equals.
So over experimentation, he figured out this equation like a law.
I don't know if he figured it out.
Right. He may not have figured it out, but he used it and basically he'd have the big wire made roughly the right size, and then he would connect sort of like a potentiometer. He would use the big wire as
what's called a center tap, which is connected in the middle of your, basically think of the transformer like a resistor or a potentiometer, where you have a wiper in the middle that's moving back and forth, and it allows you to change the resistance.
Right. And basically in just looking at it, it's changing the distance between where the say one side of the circuit comes in on the end of the big wire. The other side of the circuit could be all the way at the other end of the big wire, but you can move it closer along that turn.
So it changes the length.
Right. It changes the actual length of the circuit, thus allowing him to tune it to the larger thing. And then once he would have a meter on it or whatever, reading what was coming out of the smaller wire that had 10,000 turns. And when the freaking thing started pegging up, the meter would just be like, blam! And he was like, okay, I'm getting tuned, So, I think that's...
Why don't we all use those things?
I mean, don't they tune transformers in that way or not so much?
That's going on. Transformer. That's a whole different rabbit hole. Yeah, they do. I mean, so there's...
Keep up in the mic, buddy.
Sorry.
Yeah.
There's...
Yeah, G-Man.
As far as...
We need to hear your voice.
As far as transformers... of course, they're going to tune them so that they're not resonating at, say, 60 hertz or whatever frequency you want to use them at, because that can cause destructive resonance in the circuit. But there's also a lot of material science that goes into the core of the transformer as far as how it affects the resonance,
Okay.
the efficiency of the transformer, certain things like if you're using it for audio, or if you're using it for just a general power supply, or if you're using it for some specialized function.
Those you're driving down the road and you see all this gigantic electrical crap in a gated. What the fuck is all that stuff?
Tell us about all that.
Yeah, so typically what your typical substation.
Yeah, I always want to break into one of those and find what the hell is this
Yeah, you don't
shit?
want to break into that because basically you have probably...
Get shocked and die.
Yeah, you probably got like 11 to 19 kilovolts coming from the power station to that substation, and what they'll have there is rows of giant oil capacitor tanks and transformers.
Those PCBs or whatever.
And so what they'll do is they'll step it down. They'll run through capacitor tanks they use the capacitor tanks to affect the basically the load on the system.
Okay.
So what they want to do is try to balance the load between the output at the power plant and where it's being received.
Okay.
So that there's high efficiency.
Right.
So it's kind of like in a guitar amp where you want to balance the output impedance of the amp with the impedance of the speaker, so that you have full power efficiency, basically. And so they use the capacitors, those big capacitor tanks, for optimizing power efficiency at the substation end. And there's also what you'll see is big square rectangular tanks with giant
Yeah.
electrodes going into them. What those are
ceramic
is big
babies?
oil-filled shut-off relays. So it's a big oil-filled tank with a metal switch submerged in the oil, and so if there's like a break in the line or some kind of short in the line,
it'll open.
They can break that connection. And the oil is to keep it from arcing because there's
Right.
so
It
much power
immediately.
going.
Yeah.
Yeah,
it's-
oil is a
Great insulator. Yeah. And they also have stuff at those places like line to ground fault interrupters.
Okay.
So basically, it's monitoring the power on the line going to some row of houses.
Right.
And say a tree branch falls on the line and shorts the line to ground, it can detect that short to ground, and what it'll do is it'll pulse the line so that it's actually burning the tree branch off the line.
Oh, that's badass.
Yeah, it's awesome. So if you get like a momentary power fluctuation at your house where it's like boop boop boop,
Yeah.
and then it comes back on, that was the interrupter burning that tree branch off the line. Or burning or burning that squirrel off the power pole. Yeah. Ba, ba, ba.
Wow.
It's pretty awesome.
That's freaking cool, dude.
Now I'm gonna think of that every
Yeah.
time the power flickers.
Yeah.
Well,
Some
something
got
just got
burned.
fried.
Yeah.
You fired.
And they're set up so like after a certain number of interruptions, if it can't burn it off, it just shuts off the line. So
Okay.
the crew comes
So that's
out,
why
checks
it's
it out.
sometimes like say
It'll bup,
yeah,
and
you'll
then
hear
off.
you'll see it like tee, and then
Yeah.
you lose your power.
Yeah.
Yeah, and then the
Damn
crew,
it.
they'll get a signal at the main power facility. They've got, typically in every city, they'll have a main power facility where it's like NASA, where you've got giant screens on the wall and all these rows of terminals, and there's people sitting there. It looks kind of like something out of James Bond, a Russian spy facility or something. They got maps of the power stations and all this, and they'll get a signal there from that ground fault interrupter that says, "Hey, this line's down. You need to send a crew out to check out what's going on."
So the next time I'm actually trying to beat the first Zelda on the original Nintendo, and the power fluctuates, and I lose my entire save game. I'm like, damn it, you fucking tree branch!
Yeah. Or squirrel.
Or squirrel.
Squirrel.
Gotta start over.
So this is a question I've been wanting to. I argue this point all the time, but in terms of the power systems like that, we don't actually have an infrastructure problem, do we? Because it's all private company managed, and they keep that shit. I mean, we have one if there's like some gigantic Carrington event, right?
The problem I see is that it's centralized.
Okay.
So if something goes wrong at the facility or on a main line or something like that, everyone's affected. Whereas if we could, if everyone had a little power station at their house,
okay, yeah, a decentralized,
it's a decentralized.
But in terms of when people talk about crumbling infrastructure,
I mean,
it isn't government controlled. It may be large
There's co-ops.
corporations. and stuff,
there's
but
co-ops. It depends on your locality. And all that. So everything.
That's what I mean,
Some places have co-ops. Some places have, like Austin, we have the LCRA, which controls Austin, but also like a lot of South Texas as well.
Right, but basically these people, it isn't government controlled, and these are big companies that make their money by being able to sell power to people. So they keep the systems relatively up to date so that they can fucking keep making money, right?
For the most part, I would think so.
Because you hear in Europe,
it's more. I think the infrastructure thing is more like bridges and roads.
Right. That's what. But in Europe, they have this problem because it's the power generation is all very, very governmentalized.
Well, yeah,
and they talk about crumbling infrastructure, and because the government doesn't have an incentive as much as a private company does to go in there and freaking keep replacing shit.
Yeah, and part of the problem there also was that before the EU, and still today, every country over there has their own electrical code.
Right.
It's not a standardized electrical code. You go from Texas to Mississippi to Montana to wherever, it's all the same frequency, it's all the same power, it's all the same plug. You go from France to Germany, 50 miles across the border, it's a different plug.
Right. So that's one good thing about being centralized.
That's one good thing about being centralized, but at the same time, it's more like you need the standardization.
It's a standardization.
But you need a decentralization as well.
I would love to have decentralized, but like we were talking about 0 point, just everybody having a little wristband that fucking is connected to infinite power.
Infinite power. One day.
All right, we're gonna take a little break.
Yeah.
And come back and talk about more science.
Yeah.
More science.
Snake break, bro.
Snake
This is
break.
your first snake break.
Snake
break.
break. How do you feel? We got any snake snacks?
Snake snacks.
Snake snacks?
No, but would you like a snake five?
Yeah.
It's a high one.
High one.
I won.
All right.
Give me a snake. Give me a snake. Snake me off a piece of that snake snack bar. Welcome back, folks. Snake Bros. Hanging out in the 10 by 10 by 10 tangent cube of science by three snakes today.
3 snakes deep.
3 snakes deep. We've been talking about some electrical stuff that I don't completely understand yet.
It's cool. No one does.
Yeah, good. It's a good deal. It makes me feel better. But I wanted to ask you about capacitors. Like we had talked about.
How do they work?
Yeah. What the hell's going on? Like,
How come none of those things are touching and it still fucking works?
you had mentioned capacitors, but we're they're basically like plates that are really close together. One is charged and the other is charged negatively or something like that. By like how does that take place? They're like separated by an insulator, yet you can transfer the energy across them.
Yeah, so take the easiest case where you have 2 flat metal plates that are separated by a distance. Insulator in this case would be air,
Okay.
which is a pretty reasonable insulator unless it's wet. So in that case, when you apply a voltage across it, you have a potential between those 2 plates.
Huh.
And so because there's a potential there, you have an electric field. So kind of like a gravitational field. There's an electric field that's being generated there, and there's energy in that electric field. And so when you remove the potential, that electric field will release that energy as it degrades, basically.
Oh, okay.
And it may not be exactly the right way to describe it, but it's so you basically have energy stored up between those 2 plates in the electric field, and that's what the capacitor is providing, is that energy stored up.
So what's an electric field? Like, how do you get a field? What?
It's kind of like magnet lines.
Not really known.
That's if it is, I don't really know.
Yeah.
It's.
I mean, is it photons or is it going to be electrons?
I don't know.
Yeah.
I really don't know. The as far as my understanding goes, it's the potential between 2 sources, or a source and its.
So once again, like you were describing in the first segment, when you give something a charge or you energize it with a charge or whatever, that's like lifting the stone. Mm-hmm. And so and that's going to be in a conductor. And so a conductor that's near enough to be within that field will polarize the other way, like creating that potential difference. Is that?
It's kind of a chicken or egg thing, like that's like a magnetism electricity thing, like what creates what. but I to make sure I'm understanding your question, so if you have, say, a electric current running through a wire and then you have another wire next to it, that first wire is generating a magnetic field which is inducing electrical current in that
In the other wire. Yeah.
because there's a magnetic field moving, which is creating electrical field. So going back to the electrical field, or the the electrical field generated by the potential, the electrical field and the magnetic field go hand in hand.
Okay.
So they're always right angles to each other. And so, kind of hard to keep my train of thought here, but line.
Check, please.
Check, please. Sorry.
So you have I guess what I don't know. I'm trying to. So the electric field and the magnetic field are considered the same thing.
They're not
They go
considered
hand-
the same thing. They go hand in hand.
And
Okay, and one is
they're always
at right angles
perpendicular.
to the
They're
other.
always perpendicular, right angles to
Yeah.
each other, but you don't have one without the other.
Okay.
You never have a magnetic field without an electric
This
field.
is why it's called the electromagnetic spectrum.
Exactly. An electromagnetic wave.
Right.
Because you don't ever have one without the other.
Okay.
So going back to the potential difference, okay, the
The potential between two
potential
plates.
between two plates. So, reading some of Tesla's patents, he talked about the potential in terms of like a wound spring almost. Like he would describe it in those things. Like, so you imagine winding a spring on one end, the other side wants to.
Wants to turn.
Right. So you have that potential energy.
Yeah.
So like it takes energy to get this side wound.
Yeah, like it
And the-
takes energy to lift the baseball.
Right. So you have these two plates that are not touching. They're separated by an insulator, and you give one of the plates an electrical charge, and the other plate being near it.
Well, so it's not being near it. It's the fact that it doesn't have. So one is being filled with electrons, whereas the other is not. And
Right.
so you have an
You have a
imbalance
difference.
of charge between the two.
This is like ionization. One is being ionized in some way. It's no.
I don't think it's really ionization.
Because doesn't that mean basically that you're giving it a negative or a positive charge? That's what an ion is, right? It's something that has a more negative or more positive charge than it normally does in its normal state.
Yeah.
So if you're filling up a metal plate with electrons, that's not ionizing it somehow, because it's floating in a field as opposed to joining the atoms. Are we getting into stuff that like this isn't really understood?
I don't think I know enough about it.
Oh, okay.
So,
Well, I've asked a lot of people these questions.
yeah.
nobody
knows. Okay, well, that makes me feel better.
So the way I've tried to imagine this, using this spring analogy, is if I charge one plate, it's like winding the spring, and the other plate
Is being held still.
right.
Yeah.
So I've created that difference, and then
Yeah.
when you throw AC current there, you start oscillating the polarity
Yeah.
in the one plate. The other plate does the opposite polarity. It goes back and forth the opposite polarity.
Does a capacitor really work with AC?
Yeah, so it works differently with AC and DC. Typically, depending on the value of the capacitor, so the farad value of the capacitor, it will pass AC at a certain frequency.
Okay.
So typically, in like an audio circuit, you'll have a capacitor going between two stages to block any DC bias between the two stages. So
Okay.
all you're getting is the AC audio signal going through.
Okay.
And you're blocking any DC bias that would create noise or an offset in the next stage of the system. So for DC, it's like winding up the spring. Whereas with AC, it's a function of frequency.
It's like bouncing the spring.
I'm struggling.
really.
I'm struggling to find an adequate analogy for it, because so basically, I hate to describe it like this, but for a capacitor, you have in AC terms, you have what's called a time constant. So in DC terms, the time constant is when you charge up a capacitor and short out the terminals, how long does it take? If you short out the terminals with the resistor, how long does it take to discharge?
Okay, yeah. It's fast.
Well, it depends on the size of the resistor
Yeah,
and
right.
the size of the capacitor. You can make it last a long time if you want. In AC terms, the frequency of the AC signal that you're sending into the capacitor affects how the capacitor behaves.
Okay.
And so basically the time constant is 1 over the frequency times the capacitance value.
Okay.
And so as you go higher up in frequency, it passes through the capacitor easier.
Right.
So you're not with AC. You're not so with DC you'll typically use a capacitor to hold a voltage constant.
Right.
Whereas with AC you're using it to filter
Okay.
something.
Right. Yeah, because I know like with car audio systems, which are all DC, you put a capacitor in line in between the amplifier and the like a subwoofer or whatever, and it kind of normalizes the
You're saying between the output of the
Amp.
car amplifier and the input of the speaker.
yeah.
So that would be more of like a filter. Like a
But it's
cutoff
also
filter.
like an AC system because of the oscillation of the signal.
Yeah,
That's what I'm saying. It's more of a acting like a filter at that point.
of
Than
acting like a filter.
Yeah.
It's not like supplemental.
It'll act as both a filter and remember in the previous segment when we talked about how they're using capacitors in power situations to regulate the line load.
Right.
So you're basically regulating your speaker load with that capacitor as
so
well as filtering.
It's regulating the speaker load, not the. I always thought it was something to like sort of relieve load from the actual car system. Like the capacitors have a bunch of juice in it, and like the speaker wants to draw a bunch, it pulls it from
And
the
that's
capacitor
part
instead
of the load
battery.
regulation.
Okay.
So that's when you start getting into non-real power.
What? Sweet.
Yeah.
Sweet.
So
Back on
that's
familiar
some
ground here.
other stuff there. Yeah. So non-real power. That's a whole different
pulling it
discussion.
straight from the spirit realm. Sweet.
So in DC, when you talk about power, so your voltage times your current, like watts, which is your power output, your horsepower. In AC, there's a real and a non-real component to that.
Okay.
Because you have capacitors and inductors in the system which are differential in behavior. They're not linear.
Okay.
And so it changes the whole behavior of it.
Right. But in DC, it's something else. Like how does non-real power work in DC? I mean, if you
There is no non-real power in DC.
oh, okay.
Yeah. So it's only in AC. And so in some cases, you will dissipate power into the capacitor, but in other cases, because of the non-real factor, the capacitor will actually dissipate power back into the system.
Right. Okay.
And the same with inductors too. So if you're looking at it, it's kind of a square root of 1
Okay.
type of situation. So if you look
Square root of -1.
if you look at a chart of voltage and current in X and Y, when you start getting into negative voltage in the AC and negative currents, that's when you start getting the non-real
Right.
numbers in
Okay.
those other 3 quadrants that you don't see with DC.
Right. Okay.
Basically.
Badass. I completely didn't understand any of that. So I wanted to ask you about something else.
Cool.
I've looked into piezoelectricity and the piezoelectric phenomenon a lot, and have tried to understand that. And I think that I have a pretty decent grasp on it. But I wanted to get what your thoughts are on it, or how you understand it.
Okay. So we'll start with the structure of a crystal. So a crystal is a very set atomic structure. It's locked in place in usually a qubit form or something like
Yeah.
that. So you have molecules that are locked into a specific structure, and they're typically uniform.
Yeah.
And unless you have some impurity in
Right.
in the crystal or something like that, it's going to be a uniform structure until you have another crystal come in or some kind of fault line or
Yeah.
some kind of nucleation occurs.
Yeah.
So starting with that, you have so from what I understand, you have basically an electric field created by the atomic structure, which is the atoms and their electron cloud, which is very rigid in this crystal structure. So when you compress it, it causes... So say you have a bunch of spheres next to each other. When you push them together, and they're perfectly nested together in, like, say, a cube form or something like that.
Right.
When you push them together, one ball is going to squirt out.
Yeah.
And so...
Like displacement or whatever.
Displacement,
Okay.
basically, yeah. And that's...
Yeah, because
that
they're
may not be the best analogy
And because
for
they're
it, but
geometrical, like a flow can be created along.
I don't think it's necessarily a flow.
So you think they exchange electrons when they're flexed like that? Like some electrons are
That's-
being...
yeah, that's what I
Yeah,
was-
they're being released from that structural bond, basically. The energy of those atoms pushing past each other or being squeezed together is allowing electrons to be released.
So what I've wondered about is when you, say, resonate or flex the crystal, is it known, like, is there a way to figure out which side the charge is going to be on and where you see what I'm saying? Like, how do you know what the polarity is when you...
That I don't know. That's just...
As I've always wondered about
Yeah,
that.
I
Like,
don't know.
Crystals
know.
usually have an up and down, though.
Yeah, there'll be a grain to the
Yeah.
crystal
so it would be
structure.
something based on the crystal.
Like if you think of just
So,
if you think
yeah.
of just a quartz crystal or whatever, it's got a bottom and
Yeah.
then a top, and like I assume that.
And that's what I assume too, but I don't know. Like
Yeah,
if
yeah.
I hit the crystal with a hammer on the side, which way is
Which
the
way
positive charge?
Yeah, I don't know. And that may also depend on from which direction you hit it from. I don't know.
Yeah, that's always been a
That's an
fascinating
answer I
thing to
don't
me.
have.
Yeah, you know the little click lighters use that. That's what it. The
Right.
click is a little hammer hitting a crystal, and it makes that shock.
Yeah, and it seems to me like such a powerful
Yeah.
thing because, like, you know, like the little grill starters or whatever, you take it out and you hit it.
Shock
And it's,
yourself.
it's a pretty good, pretty
I
good
remember I
jolt.
got in trouble once in elementary school for taking one of those to class.
Hitting people on the
and
neck.
I was like getting people to all touch together and bam, get everyone down the line. And then the teacher took it away. You know your son is shocking people? Yeah, it's fun.
Shock factor.
Yeah. Shocking behavior in school.
So yeah, I it seems to me that has that we should be able to use that, and it's weird. I mean, maybe I'm like way off on this, but
Are you saying that it has potential?
yeah, it has great potential. So well, obviously they use that's what's in circuit boards, right? They make these circuit boards out of
Silicon.
which is piezoelectric, and so that you can, you know,
Well, so silicon's more of an insulator.
Right, but so is quartz and stuff if you're using it right.
Right.
Yeah.
Yeah.
Is that's what
it's just interesting that it goes
Yeah.
both ways. Like you can hit it with a hammer and get the electric charge, or you
Yeah.
can charge it with electricity and it
It will
will
flex.
vibrate.
Flex.
Yeah.
So that's how I thought circuit boards worked. Like the reason why they're using the crystal is because that's how they can get like solid state.
So that's a whole different thing. So what they're doing
Get up in the mic. buddy.
Sorry, that's a
It's
whole
all right.
different thing. What they're doing in the case of solid state electronics is they're taking silicon, not silicone, that's a totally different thing. They're taking silicon and other crystal type elements, and they're what they call doping them. So they're either impregnating them with extra electrons
That's dope.
or removing electrons from it when they make it. And so in that case you'll have, like in the case of a transistor, you'll have a layer of extra electrons, a layer of no electrons or fewer electrons, and then another layer of extra electrons.
Okay.
And so when you feed electrons to the middle, it turns on the switch and allows electron flow through. But when you don't feed it, it neutralizes that middle zone and doesn't allow flow. That's easy way to describe it.
That sounds similar to like a capacitor. Like they've got these 2 layers of different charges.
Yeah, but he's saying that this stops the flow. Like
this stops
right.
the
No,
flow.
I understand that they're using it as a switch, but it's this. It's like, it sounds to me like they're taking the same principle that works between the potential between 2 things and using it as a switch. Is that not right?
Yeah.
Okay.
Because when you have that positive layer, or you have NPN and PNP transistors, so positive, positive, or negative, negative.
Yeah.
And so
that's freaking badass.
Yeah, it's pretty crazy. Like, can't imagine being the guy coming up with that stuff. Like, so if we put extra electrons in this layer, but take some away from this layer, but then put more in this layer.
Yeah. And that is ionization, right? I mean, isn't that?
Yeah, that's that like.
Because you're making ions if you're adding electrons to it.
Deposition.
Yeah.
So, yeah.
And the positive charge is caused by the protons. There's an
Positive
imbalance.
charge is a absence of electrons.
Right, because the protons.
So protons are always there. It's in the protons are in the nucleus, right?
Right, but yeah,
You're not changing that. You're changing the number of electrons in the cloud around the nucleus.
Right. So I'm not saying the protons are flowing, but the protons are considered, like atomically, the protons are considered to be positively charged.
Yeah. And so what you're doing is removing electrons, so the positive charge becomes dominant.
Right.
That's the winding of the spring, basically.
That's the winding of the spring.
Getting the electrons to move away from
one side.
Right.
Yeah.
Yeah, badass.
Yeah. And so in the case of the Earth, like with your power system, the Earth is your electron sink.
Right.
All your electrons are in the ground, in the Earth, and then you create a potential, raise the baseball away from the Earth. All the electrons are down there.
Right.
And so
It wants
So
to get.
that's what grounding is. Like you
that's
connect
what's
it
grounded.
to
It's
the,
getting back down to the sink.
And so when you're shoving that copper grounding rod into the ground, you're not plugging into the dirt. You're plugging into a big electron field. of
Yeah,
the
you're
Earth.
plugging into the basic, like y'all said, the big steel ball that is the
Right.
Earth. Yeah. And then we're raising that baseball way up at the power station.
Yeah.
Running it down the line to your house, and then you're dropping it at your house
Right.
onto the ground.
It drops through all the bullshit at your house. Thump,
to the ground. And
So-
rolls,
through your
back to the
microwave,
power station.
goes over
Yeah.
your TV. It drops down to
So
the
we've used the argument, like we've talked about the Nikola Tesla's wireless power system, okay? And there's a lot of people that say, oh, it can't freaking work. You can't transmit power from that distance without wires and all this kind of shit. And we've used the argument that, well, one side of the circuit has no wires today.
Well, it's because the other wires.
Right, but that was half of his system.
It's wireless.
Yeah.
That's the other half, right?
Yeah,
I mean,
that's
is that
the
a
other
valid
half.
argument?
Yeah.
that
Yeah,
it is.
absolutely,
Yeah,
yeah.
half
So
of our
he's-
current system is wireless, and that's what when we're
ground.
plugging into
Yeah,
the
what we're
ground, it's
standing
going.
on. Yeah.
You
So
can technically consider it to be going all the way back to the power station.
It's half wireless, basically.
Right.
Our system now is half wireless.
Right.
Yeah.
So there's single wire system.
Single
yeah.
wire system.
Yeah. So there's nothing. So in Tesla's fully wireless system, basically the other wire is going to be a certain layer in the atmosphere. That
with
would-
an antenna that's picking up a resonant frequency.
Yeah.
Right, and also he was thinking if he could, quote unquote, charge that layer,
That layer,
enough, it would ionize throughout the entire world and be able to become a better conductor. From what I
can see it.
understood,
I can see that.
he built a test model of it, and he got this tube, an actual tube that he could put a gas into, like a noble
It
gas.
should be powered in tubes.
Right, and it was 50 feet long, and he put a gas. The gas that he filled the tube with was the same basic makeup of this
the ion
layer in
layer,
the atmosphere where where the Wardenclyffe Tower was basically reaching up to.
Yeah.
So he fills that tube, 50-foot long tube, and I don't know how big around it was, full of this gas, and then he uses his, I don't know what you would call it, transformer, the Tesla coil, high frequency, high potential.
His oscillator.
Right, electricity to, like, he charges one side of it, and at first on the other end he wasn't getting a flow out of the other end. It took a little while, but it ionized the gas.
It had to travel.
Once it had ionized, eventually all of the gas in the tube became ionized and became a ridiculously badass conductor, and he got the shit out of the other end with like very little resistance whatsoever. So if you could put enough power into this layer of the stratosphere was his idea. If you could get enough of it there to ionize, it would eventually be a chain reaction and ionize the whole thing all the way around the globe. And then he talked about after that takes place, then you could do certain things where you could light up the sky like a light bulb.
Yeah, like a night light.
What are the bulbs called that are just full of gas? Yeah, fluorescent. Yeah. You could basically choose a place and just light that area up at night, and it would just be like a big fluorescent bulb just shining down.
STS-80.
It's freaking badass.
Yeah, the shuttle mission that dropped the tether. That would be the easiest way to power it up, because I mean, like generating that much
charge it up.
Yeah, generating that much juice from a power plant might be really costly. But if you just drop that tether from space, and let it drag through the freaking stratosphere and just charge it up.
Yeah,
because that tether pulled so much freaking juice. I mean,
tell the story of what you're talking about.
Yeah, so there was it's STS-80, I believe, is the number that the shuttle. They did this experiment where they had this incredibly long tether. It was basically a cable, and you can watch videos of it where they got cameras watching it, and they had to drop it because they unreeled this tether from the shuttle. And it's going down miles and miles, and they start dragging it through the upper atmosphere. And as soon as it started to hit the upper atmosphere, it almost shorted out all the systems in the shuttle. I mean, all the freaking meters in the shuttle went pegged to the other side and everything. So they had to eject it immediately because it blew circuits and shit and fried a whole bunch of stuff, and it almost made it dead in the water, dead in space. So they eject it. So the video you watch...
Dead in the ether.
Yeah, dead in the ether. The video you watch is the tether has been released, because obviously there's no video before that, because it freaking erased everything.
Jeez.
You see the tether, and they're watching it in infrared, and it's just falling very slowly, and it's this incredibly miles and miles long, and it's going down into the atmosphere, and it's glowing like crazy, because it's just freaking pulling... It's pulling like freaking... I don't even know what the...
Well, and it's basically connecting the potential between... two layers of atmosphere.
Dude, it wasn't even two layers of atmosphere. It was pulling juice. Well, this is the theory that I saw directly from the solar wind and just plugging it down into the atmosphere.
Oh man.
So that was the capacitor, solar wind to like stratosphere.
Yeah. Ladies and gentlemen, NASA has short-circuited the Earth.
Yeah, that's right. And the sun just goes bzz, 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 goes out.
Holy cow, that's awesome.
Yeah, so that would be the way to power it. And the other weird thing, if anybody goes to watch that video, is all the freaking UFOs that start flying around it.
Yeah,
really.
I mean, there are freaking hundreds of them. Like
those little.
Yeah, they're discs that have a square thing taken out,
and it's kind of like a pucker and butthole.
They're going. They look like little space bacterias.
Yeah,
and they just start surrounding that tether. And it's crazy. Yeah. Yep. STS-80. They never tried it out again.
Damn it.
Well, should have put an insulator on that one, guys. Maybe a rubber pad between the crank and the shuttle.
I know, guys. Let's directly connect the sun to the Earth with the shuttle in the middle. That's a good idea, isn't it?
Hold on, let me stick this fork between the prongs.
Yeah. That seems like the way to do it. I mean, what was the Tesla? In one of his speeches that I read, he gave the information of how much power the sun pours into the Earth's atmosphere.
It's like 160 petawatts continuously or something like that. Petawatts.
Yeah.
What's that?
Petawatts.
Peta is 10 to the 12th.
Yeah, it's
right?
like
so 160 with 12 zeros after it.
Yeah.
I could be wrong. It might not be 10 to 12.
We get shit wrong here all the time.
It's a
Don't
big
worry,
number.
Jimmy.
It's
a ridiculous amount of
Isn't it
energy.
one more magnitude beyond giga? Like,
Yeah, I
there's
think so.
gigawatts and
And
then
then
it's
petawatts,
petawatts. So if a gigawatt, like a megawatt is,
10 to 6, 10 to 9, 10 to 12.
yeah.
Okay, that's reminding me of something else I read. I think it was Tesla talking about it. But so there's all this basically electric charge coming down
Yeah.
and hitting the Earth. And the atmosphere acts as sort of like a resistor between, because the Earth is like the sink.
And it's layered too.
Well,
so
I
it's-
would see it acting more like a capacitor.
Well,
Like
for that
two
energy
plates,
to get
basically.
Yeah, for that energy to get all the way down. What was I? I'm trying to figure out what it is.
It's both. It's both because the layers of the atmosphere will gather that energy, but it also is like sort of insulating
Yeah.
the surface from the.
Yeah.
Yeah.
So and I'm sure there's some inductance somewhere, probably from
That's-
the
yeah.
core of the Earth.
It's called lightning. No, those are the shorts.
Well, I mean, we got the big inductor, which is the core of the Earth,
Yeah.
creating our magnetic field.
Yeah.
So
So like when lightning strikes,
that's a line to ground fault.
Yeah.
right?
it's
And
short.
so in that area, it ionizes everything, right?
Yeah, it ionized. Basically, what happened is the potential built up to the point where it arced.
Right. In other
So
words,
like when we built that little spark gap thing here, where we're charging up, and then
Yeah.
that's the same thing.
it's
just-
building a tunnel of plasma through the atmosphere.
Yeah.
To make a
It's
to make a
basically built up
conductor.
enough energy to punch a hole of plasma through
Okay,
to the sink.
That's a good question. Like, how does
And we're gonna stop right there. We gotta take a break. Just keep that question in mind.
Hold that thought.
We're gonna take a break.
how does
Yes, I've been waiting to be able to do that. Damn it.
How does your snake snack?
got me back?
All right, we'll be back with Snake Bros in the second hour. See you guys.
Next. All right, we're back. It is now the next day, and we partied our asses off last night. And I don't remember what my question was.
It was a long snake break.
That was a long break with many snake snacks. So, yeah.
How does?
How does
something?
how does electricity work?
Well, I did have a question. We were talking about piezoelectricity, and I wanted to get your thoughts on, like, that people see earth lights and stuff that are associated with earthquakes, right? So they see little balls of lights and everything, and animals go crazy and shit, like long before an earthquake happens. And some people have speculated that might be like the coming earthquake is causing all these stresses in the ground, and there's crystals down there, and that maybe piezoelectricity has something to do with these weird, like, balls of light that appear on the surface and sort of float around right before an earthquake. What do you think about that?
It's very possible. Another factor could be that the shifting plates is also affecting telluric currents in the crust.
Yeah.
I see that to be more
Yeah.
likely, because I mean that would have to be some really big crystal chunks to do that.
What are the telluric currents?
The
What is-
telluric currents are basically electrical currents that are running through the surface of our Earth,
Yeah.
of our planet.
If you look at any kind of map of the magnetic field, it's kind of regular on the outside. It's this big like figure 8 on its side. But once you get below the surface, it's really complex and knotty and stuff. And there's like weird currents that flow through it.
And they actually understood enough about these currents to use them to transmit telegraph signals back in the last century.
Really?
Yeah.
Tell that story. I don't know.
So that's really the gist of it, is that they would. I'm not sure how they would find them.
Yeah. But did they put the wires in the ground? I mean, like, how did they use it to actually transmit?
I believe, they would. Yeah, I'm not sure if they would put the wires in the ground and use the telluric current to transmit, or they would run their line along that telluric current, so they knew the return signal would be a good low impedance return.
That's cool.
I don't know.
That's
I'm not
cool.
sure if it's.
I'll have to look that up because that's badass.
Yeah.
I know that the Carrington event really, because of telluric currents, like got into the telegraph lines, and they were like shocked. It was like shocking the shit out of operators.
Yeah.
And there were some like where they shut all the breakers down and everything, and then the whole station was still active. It was still powered.
Now is the Carrington event the
huge solar flare that hit in the 1800s?
That's what I was thinking. Yeah.
By the way, that reminds me, I was gonna talk about this yesterday, but we had the big break. But right now there is a humongous, many times Earth-sized sunspot on the sun, and it's facing right at us. I mean, it's like ridiculously gigantic.
Yeah, I saw that in the news.
I was looking at pictures of it. It's huge.
Apparently, it could be, if you could look at the sun, you'd be able to see it.
Yeah,
it's that big.
Yeah,
wow.
Yeah.
I
was thinking of getting some polarizers out at work.
Yeah, well, I have the telescopes up there, and I use a welding lens, and you can fucking see that shit.
That's cool.
Yeah.
I had just read a story that we were like at a solar minimum. What happened?
Yeah, that's one of the things in the story was like, this is a solar minimum. There's not supposed to be anything in there, and yet there's this gigantic fucking hole in the sun right now.
Was it like that other one that was like covered half of the, when it was facing us, it was like pretty much all dark?
No, this one's in a big circle. But like if you look at the sun's face, I can't obviously because this is like audio only. But if you look at the sun, like imagine the sun is a quarter. Okay, it would be like the size of the eye on the guy on the face of the quarter. It's pretty fucking big compared to the whole face of the sun.
Wow.
That's a big ass hole.
Bigger than our planet, right?
Yeah, it's many times the size of Earth. And they were saying that like if it releases a flare, it'll be an M class, like the kind that caused the Carrington event.
So all our cars will be screwed.
Yeah, everything,
all
computer,
our phones, everything.
Yeah, the whole power.
And this podcast will be useless.
Podcast will be
So if you're listening to this, it hasn't happened yet.
Yeah, I've wondered what, like, if some M class flare hit us, what that would do to solid state memory.
It'd probably be extremely destructive.
Yeah. Yep. Because that depends on like little tiny capacitances between little plates of things, right?
You're talking layers of atoms.
Yeah.
Where they're counting the layers, the atoms and the layers and putting down for those transistors.
Yeah, I think that would be messed up by a Carrington event.
Yeah.
Yeah. Shit.
Damn. Well,
start carving it into stone.
Yeah.
Gonna be fucking stone casts.
Yeah. Stone casts.
Got a big stone drive. Well, is there any other thing else you wanted to? Because I had another
No, go ahead.
Side topic.
Yeah, side
not about
topic.
electricity specifically, but I wanted to talk to you a little bit about the stuff you do with 3D printing and drones.
Yeah, this guy 3D printed himself a 3D printer from a 3D printer from his work.
And then 3D printed a drone. That's fucking badass. So, yeah, I don't know like specifically, but just the idea of 3D printing, like where do you see that going in the future maybe, or I don't know, what are your thoughts about it? I think it's
going to be huge.
It's going to be huge.
It's going to be huge. No, I think, it's something that's definitely still in its infancy as far as people being able to do it at home. I mean, there's companies that have been doing it since the 70s.
Yeah.
Doing more the not so typically the cheaper end where you're going to find stuff at home is like your glorified hot glue gun version of a 3D printer.
Okay. But are we going to end up where I can go up there and be like, beep, beep, chicken, and get like a fucking chicken out of the...
I would hope so. I mean, ideally we want replicators, right?
Yeah, exactly. Replicators.
Yeah. So I would hope, eventually we get there.
Yeah.
Chicken, good.
Chicken, good.
Chicken.
You know, like your home 3D printer's probably going to be the hot glue gun version.
Right.
There is a company called Formlabs that was bought by one of the larger companies that does make a commercial user version of the, I can't remember what the exact method is called, but it has a pool of liquid epoxy basically.
Okay.
And it uses a laser to draw the pattern of the object
Oh, wow.
onto the epoxy, and it hardens where the laser draws, and it draws that part out slowly. So it's doing the layers with the laser as it draws the part out of the.
Oh my God, that's kick-ass.
That must be cool to watch.
So the company's called Formlabs. You can link to their
Hell
link in
yeah.
the show notes. It's cool, really cool to watch.
Wow.
But that technology's been around for a long, I think since the 70s, mid 70s, and so there's like two main companies that have like industrial 3D printers that
I did see when
use.
I went. Do you remember when I went to Vegas for the commercial graphics convention? I drove with that dude.
know.
Well, it was
a long time ago.
It was a long time ago, but I went there, and one of the things they had on display there, and of course this is showing all the next generation technology. So, but they had this thing on display there, and there was a big, like a vat, I guess it was a cube, and it was clear.
Science cube.
The science cube, and it was clear with some kind of clear, I guess epoxy or something in it, like. And they had this machine and there were two lasers, right? And so they would wherever they met inside the epoxy, like they're flying around it, and they would build something. On the inside
so it's not even like lifting it out. It
constructs it on the inside of the liquid.
In the liquid tank.
And then the liquid would drain out, and the thing would be left there. But it was all clear. It was like this clear, yeah.
Yeah, I've seen those before. That's pretty cool.
Yeah,
stuff.
and they would build little things and give them to people that were there. It was cool. It was badass.
Damn.
But it was cool with the two lasers, so that you could get the, that was awesome.
Like the six
so it wasn't,
axis,
it wasn't having to do it by layers. It was really cool.
But right now, like the one you use, the one you have, and the one you have at work is the spools of some poly material, right?
Yeah, it's the hot glue gun with the filament, basically. So,
Does it melt it?
Yeah, it melts it.
Okay, so the filament runs in, and then it melts it.
It melts it, goes through a little tip that comes out as a fine thread of hot plastic. And I use ABS. There's PET, all kinds of other different plastics you can use. They have some composite materials, like it's typically plastic mixed with whatever kind of finish you want, like a wood finish or like brass particles, steel particles, that kind of thing.
Wow,
that's what I was going to ask you about, making steel.
Print me a
sword.
You got a milling machine, right?
We do, yeah.
Print me a sword.
Print me a sword. Yeah, unfortunately, the composite stuff right now is mostly plastic with filler material. That
need to get the
look like
the file for Excalibur.
Yeah,
the 3D printer file for Excalibur, bro.
Yes.
Yeah, you were showing me videos of your milling machine work. That was cool.
Yeah. We just got a Tormach CNC. And that thing is pretty sweet.
What is it's a laser?
No, it's a computer-controlled milling machine. So if you think of like your old grandpa's mill.
Oh, yeah.
But this is computer-controlled. So we load a chunk of metal in, and we can program in. Okay, I want threaded holes here. I want it to cut this pocket here. I want this profile.
It's got a drill tip that can move laterally as well. So
it
goes
goes sideways,
like a smithy.
Yeah. God, it's freaking awesome.
Yeah,
We're gonna build Tesla parts.
Yeah.
Okay then. Mill me a sword.
Mill me a sword.
That's badass.
Yeah, I'm still learning how to use them too.
I thought you said you also got the laser CNC machine.
We have a laser engraver that I'm working on getting up and running. It's pretty much there. It's not a very powerful one. It's only like a 2,500 milliwatt laser.
You have to wear goggles.
Yes.
Sweet.
Yes. For
You have to fucking wear goggles when you're using a laser. It's a real laser.
It's a real laser. We can engrave plastics, wood, cut thin plastics if you run it multiple passes. We
Yeah.
can cut foam, that kind of thing.
Nice. I did see it.
it's
Oh, that would be nice. Like
Yeah.
cutting foam.
Yeah.
That's hard to do with scissors.
I did see some videos of one of the newer handheld lasers. Like, they look like lightsaber handles because they're really big, but it'll pop balloons. That was pretty badass. The dude was all.
Do you know what color was it? What wavelength?
It's blue.
Okay.
Popping balloons with it is badass. Go to like some theme park and little kids are walking around and you're like.
You're making me laugh. I got allergies. Sucks. No, keep making me laugh. I'm just going to move away from the mic. I would just take that to a...
Yeah, just start popping little kids' balloons.
So, yeah, all right. So you got this huge 3D printer, glorified hot glue gun at work, and what'd you do with it?
Oh, I built my own 3D printer. Yeah, so we got it in. It's a TAS 5 we had bought, I think, about 2 years ago. And I didn't know it at the time, but when we got it, it's got the metal motor parts and, guide rods and all that. But all the rest of the parts are 3D printed. So they're 3D printing their own machines and building them and selling them.
Oh, okay.
Which is great. Great business model, great idea.
But you have to get the circuitry and program it, firmware.
Yeah. So I printed all the parts. I ordered all the motors and rails and stuff off of Amazon, and then got the electronics from Mauser. The company actually has all the bill of materials, all the parts they use online. A lot of the firmware, the control firmware, is open source. So you can download it. People provide it online. And then you just, once you get it calibrated, it's pretty much like your home printer. You just download whatever you need to print and hit print and walk away.
Yeah, and they have huge websites that are like file sharing places for people who built models, right? So you can just, if you want to do something, you can go search to see if somebody else has already made the model.
Yeah.
And then you don't have to bother with building the 3D model and stuff.
Yeah, what was that? Was it an app that you had or whatever? You were just like, yeah, look at this. And you were showing me, like, you just type in anything and just it had all of the things that people had made for 3D printing, and there was categories that you could go through.
Yeah. So there's a few different sites out there. Thingiverse is one of the big ones.
Yeah, Thingiverse, that's what it was.
I believe they were started by MakerBot.
Okay.
And then MakerBot was originally purchased by one of the big companies, I think. And so now it's controlled by one of the larger companies, but it's still kind of an open community kind of thing. I think there was some drama there when MakerBot went from open source to a real company.
Yeah.
And I think some people felt like they kind of stole the open ideas from Thingiverse.
Right. It's like, how do you
and made money off of it?
How do you buy open source?
Yeah. So I don't know. It's, I can see both ends of it, but
That stuff fascinates me though because of the free, like I've had this with the modding community, like with computer video games and the mods, right? Like there are mods that represent thousands of hours of work.
oh yeah, like the cinematic mods.
Yeah.
The Half-Life
Or like,
cinematic
yeah, like
mods,
with
there's so much work.
with Skyrim.
Yeah.
Skyrim has mods in it that put entire new stories into the existing game that you can play that lasts for 70 hours when you're playing it, that has like multiple voice actors and like all this new just it represents thousands of hours of work of labor and coding and everything, and they release versions and then fix bugs and release versions and fix bugs until it's perfected, and it's free. That shit blows my mind. It's like what other hobby can you think of where the people who benefit from the hobby is far vaster than the people who are actually involved in the hobby.
Yeah.
Like if you collect
Yeah.
stamps, nobody else benefits from that, right?
Yeah. No one benefits.
But if
You
you're
like fishing? No, you take all of your fish home.
that's right. But in the modding community, like one guy who's like caught the bug of like modding,
Yeah.
like benefits millions of people who download
Yeah.
that. I mean, it's amazing.
It
And
is
it's
amazing.
free, and they tried to monetize it. Like Steam tried to monetize it by putting it into their. They have this thing called the workshop in Steam. So any Steam game you download, it can have a workshop thing associated with it where people can upload mods. And they tried to sort of monetize that, and it was still by choice. Like the modder could decide whether they wanted it to be paid for or not, and it was always real small amounts, like 99 cents.
Yeah.
And like the whole community flipped out, and Steam was like, "Whoa!" and they backed off and stopped it like within a couple of days.
Wow.
But it resulted in a bunch of mods that would like just put random NPCs into the game that would come up and beg you for money. But they were always wearing all those rich clothes. They're like, "I'm rich, give me money."
Very much.
Which is not the case. A lot of modders are like starving artists or kids in college or whatever. But yeah, still, it was.
But
it
you
was-
can make a name for yourself doing it, and
Right.
and get a reputation
Yeah.
if you're a badass, and then you can. Ultimately, I see that it can be monetized in the sense that you get recognized for doing something that millions of people love, and then you can get a job where other
Right. There's a mod for Skyrim called Falksar that basically built an entirely new island, gives you a whole brand new story with all new characters, and you go there and it's got its own towns, it's got its own mainline story with all these side quests and everything. And that team, like got snapped up by a video game company after they released that mod. 'Cause it's so badass,
Yeah.
So yeah, like I agree. That that's,
it's like it's an investment for them.
right, and it's just like a badass, like you don't need a resume. Like you just say, here's my fucking
That's
mod.
your portfolio.
Hire me.
Yeah.
Yeah.
hire me.
Hire me now.
Yeah.
But at the same time, something you create, you should always have the right and the ability to say, no, I want to charge for this.
Right.
It's like,
Yeah.
But unless you're creating it in something that somebody else made,
exactly.
that's
Yeah.
where the difficulty is. How do you charge somebody for something that somebody else made that you just used in a new way?
Yeah.
Well, okay, yeah. So that when the Steam thing came, when they were charging, Steam was getting a little tiny cut, and then Bethesda, who made Skyrim, was also getting a cut. So it was like, so
Yeah, they're splitting the
the
deal.
modder
Right.
wasn't getting the full.
No, well, yeah, he wouldn't get the
Yeah.
full, but the modder got the bulk of it. But Bethesda got a little bit, and Steam
Yeah.
got a little bit for their work, or being involved in the system, or whatever. And it just
For our sponsorship.
because we have it where you can download it.
Yeah.
But the connecting back to what we were talking about with 3D printing, like you have these sites that just where everybody uploads their models that they've made, and some of those models they've spent hours and hours and hours on, because they're not simple, and you can just go download it for free. The sharing is really cool. I think. It's
Yeah,
really badass.
I agree with that.
It's definitely helpful when I need a quick part.
So So you built this drone? Like, okay, I just think this is funny. Like your boss buys a 3D printer, and you're like, sweet, and you print your own 3D printer and take it home.
Yeah. One part at a time, though.
One
so
part
nobody
at a
notices.
Well, no. I just bought my own plastic spools and would take them in and run our printer at night.
Yeah.
Yeah. What did you pay for the electricity?
Well, no.
Yeah, but his boss knew he was doing it.
Yeah. I know.
They knew I was doing
It'd
it.
be funny if you were trying to sneak it out there.
Yeah.
One part at a time.
One part at a time.
Classic. So yeah, you take home your 3D printer, and then what do? You print something else that flies.
Yeah. So then I
And spies on people.
Yeah. Well, this one's just a raced one.
Right.
There's no spying with this one.
But you do have a camera on it.
Yeah. It's just a little.
It's
tiny.
loud though. Like, how do you build a silent drone? I've been wondering about this.
I don't know because propellers are loud.
Yeah.
No, but they make them the
What about an
airplane
impeller?
type that are not.
Right, but those can't hover. Like, what about an impeller? Like, if it was in a cylinder and it had an auger-like thing?
Yeah, that might work.
We should try it.
We can try it. We can 3D print it.
Yeah, exactly.
Needs disc turbines. That'll
Disc
be quiet.
Right.
turbines.
Yeah. So can you? So what? Like, are you guys going to try to build the Tesla oscillating Is that what you're talking about?
The prototype will be with that first, yeah, just so we get a feel for everything, and then we can machine.
Which building are we going to shake down?
I don't know.
Maybe a bridge? Try a bridge?
Yeah.
Or you just plug it into the ground? I mean,
There was something I was planning to use. We're talking about the reciprocating motor that Tesla invented. It was pneumatic, powered by air pressure or steam, and GMA is going to print one.
mill one.
And no one.
Oh, right. Well, you are going to print it, right?
Yeah, I want to print it first and get the whole prototype done.
Oh, okay, I see.
And then once we have it done out of plastic's cheap.
Right.
And then once we have it all finalized, we can cut metal.
Like the airplane parts hanger thing that we looked at, where on one side they built the prototype pieces out of wood, and on the other side they would build out of metal when they had it perfected. Yeah, that's cool.
Yeah,
That's
and occasionally I'll run into something or be working on something and be like, that's a good thing we can use that for.
Yeah.
And then I forget. I need to write them down.
Yeah, I need to start keeping a list of all the things. Like, oh, I need to print that. Oh, I need to print that.
Yeah, like the back of my
Oh, I
phone.
need to print that. Yeah, like the back of your phone. It's like,
Still
you
broken.
need to
Yeah.
keep a list of it all. 'Cause
Yeah.
It just
I'll
keeps
definitely send you
expanding.
I'll definitely send you a file for that.
Okay.
Because
I have that problem with my printer. Whenever I'm home, I'm like, I know there was some shit I needed to print.
I needed to print.
yeah.
It's just a laser printer, though.
Yeah.
So when
Prints lasers.
when I worked for Prince Lasers. When I worked for LCS up in Vermont, they had a printer that I don't know if this is like sort of prefaced the 3D printer, but it used blocks of material. It was a color printer. It was like full color badass, like, but you had to turn it on and wait for it to heat up because it had like a big yellow cube and a red cube and a blue
It's
cube.
like a wax base.
Yeah, and then like you put them into these little like compartments and you closed it, and then you turn the printer on and it would go, and it smelled really bad. It smelled like burning crayons, and you had to leave the room.
Yeah, but
And it would melt those things, and
yeah.
but when it printed, it was just fucking beautiful.
Yeah.
like it would spray that stuff onto the paper. Yeah,
Holy shit.
yeah, it was cool.
That's pretty crazy.
Yeah,
But yeah, the drone. I have a Phantom 2 that we've flown out at several properties. You know, got footage and all that. But the one I built with the 3D printer, just wanted to. I'd watch videos online of people flying the little racing
racers.
quads, little racers. Yeah, and just wanted to build one. So I looked online, looked at Thingiverse, and people that uploaded plans already. So.
and did you say it's really hard to pilot it? Like you have to practice?
You do have to practice, yeah, or you will crash. It's so I started with the simulator. The controller I got plugs in USB to the computer,
Right.
so I can just fly on the simulator, and we got it tuned to where it feels pretty accurate.
Okay.
And so I practiced on the simulator a lot
Okay.
before I really even flew it for real.
That's cool.
Like we took it off. We took it in the air out in the front yard once, and it was across the yard in half a second.
Shit,
Almost
that's
hit some
fast.
lady walking by with her dogs. We're like, okay, maybe we just need to go back to the simulator. Right now.
Didn't you tell me that you needed to check, though, the real flight to see how much like the simulator it was?
So we had to at least check it once or twice to compare it and be like, okay, is the simulator good? Can we start practicing with the simulator and get
Now, when the
our
when the
muscle
simulator
memory
runs,
right?
are you like, what is the perspective from the screen? Are you watching the drone fly, or are you looking from his perspective?
You can switch. The one I'm using, I think, is called FPV Freerider.
Okay.
That's what it's called. And it's a free one, or no, it's like a $5 download.
Okay.
Or whatever. But you can switch between third and first person.
Oh, okay.
Yeah.
Cool.
So I fly in first person just because I've got the camera on there. That's how I'm flying it in real life.
Yeah.
It's way easier than third person view.
Yeah, that's what you were telling
It's
me
like a
yesterday.
race
It's
car.
way easier.
So.
Do you go out of body? You like forget that you're standing there?
Kind of. It's kind of weird like that.
Yeah.
Like, and I also get a huge adrenaline rush from it.
Yes.
Like I'm
Yeah.
kind of shaking because it's like, oh,
That's-
I don't want to crash. Oh, fuck, I don't want to crash.
Yeah, you're like, wait, I'm on the ground. I'm not in this thing.
I'm not in this thing.
But I had that same sensation when you got the Phantom 2.
Yeah.
First time, going and flying it, it's like, it's a rush.
Yeah, and you're like,
Yeah.
am I gonna screw this up? Yeah.
Yeah. That's really
It's
cool.
fun, yeah. And
With that little racing drone, how fast does it go?
I haven't taken it full throttle. I don't know how fast it will go.
Wow.
Because, I mean, you theoretically, you could fly it
Vertical.
completely vertically. So, like, completely wide open. It's just flying straight vertically, but sideways.
Yeah.
But you'd have to be able to angle the camera.
Turn all the copters into props.
Yeah, exactly.
Shit.
But it can go pretty fast. I'm guessing it can at least go like
Man.
30, 40 miles an hour.
That makes me think like if
If
you
not
had
way
if you
faster.
had some kind of wings that could unfold. So like you get like it's a VTOL, right? Vertical takeoff and landing. You get it up there and you start to tilt it, and these wings unfold, and then when it's fully vertical, it's got like fucking wings coming out of the side, and then you're actually gliding. That would be
Gone,
badass.
yeah.
Yeah. You gotta have a tail.
Gotta have a
Damn it.
tail.
Yeah, you need to tell. Yeah, I guess not.
Oh, that's fun. It's
It
a
could
lot
be
of fun.
done.
Yeah. Well, let's go ahead and take a break. It's getting hot in here. It's getting
Yeah.
really hot in here. We're almost at 30 minutes.
Yeah, we were inside the cube and the air conditioner's too loud, and we
The
have
sun is
become
blazing.
a science experiment.
That's right. The one with the frogs, right? See if they jump out before they start boiling.
Yeah.
Well, I'm jumping.
All right, let's go. All right, snakes out.
Snakes out. All right, and we are back in the 10 by 10 by 10 tangent cube of science for the final segment of the final hour of SnakeBro's episode 15 with half a pyramid tied behind our backs just to make it square.
Hell yeah. We have brought it down to operating temperature.
That's right.
And we are ready to proceed.
That's right. So, I have a couple of things I want to talk about, and these are somewhat removed from electricity, but have to do with space. One of them has to do with space, at least. Space is it's got some electricity in it, right?
Yeah.
So on the International Space Station, I think we've talked about this before, but I want to do it on the show. This is really cool to me. They have these like opaque plastic. Well, they're translucent, so like they're not clear, but they're translucent, so light can come through them. But they're white, and they put their big square panels that they put on the outside hull, so that when the sun shines on that side of the station, on the inside, that white thing lights up like a light bulb. It's power saving, so they don't have to, right? And the Russians on their side of the station noticed that their fucking panel, their light panel or whatever in that room kept getting dimmer and dimmer, all right? And so when they went on a spacewalk, they were going out there to fix something else. One of them, he stuffed a rag in the belt of his EVA suit. So he went out there, and as he went past that panel, he just kind of wiped it off. It was grimy on the outside, so he wiped it off. And when he went back in, they tested the rag to see what the hell it was, and it was fucking plankton. And of course, the idea was that NASA immediately, because America has tons of scriptards.
Land of scriptards.
That's right, it's the land of fucking scriptards. They claim that the plankton must have come from one of the Soyuz capsules that they hadn't sterilized it properly. And the Russians were like, well, it didn't come from, because they launched from a peninsula, okay? And so there's ocean around there, and they're like, well, it's not any plankton that comes from our oceans. And still to this day, the plankton has yet to be identified with any earthbound species.
Not saying it's alien plankton, but it's alien.
It's aliens plankton.
Yeah.
It's fucking space plankton.
Yeah, that's pretty wild.
Yeah. I mean, like, you have to think of just the claim that NASA made of it being, contamination is ridiculous, because that kind of ignores the whole problem of the plankton existing in space, as opposed to
Yeah.
the ocean. And in direct sunlight, like in space, direct sunlight is
Lethal.
lethal.
Yeah.
Like,
Yeah, the
I mean,
radiation is lethal.
yeah. Yeah, there was an estimate that like a human being could survive like less than 1 minute in direct sunlight in space in near Earth orbit before you would be too irradiated to survive. Like you would have like
You're Swiss cheesed.
you'd have a class 3
Yeah.
sunburn and a
Oh shit.
And all your DNA has just been Swiss cheese.
right, right.
Swiss cheese.
I didn't know that was a verb, but now I know. Swiss cheesed. So like that kind of brings up the idea of panspermia, like the idea that life was seeded here by biology from space.
Yeah, and I was thinking recently about the whole idea of evolution. And I don't really know where it stands today because I don't look into it a whole lot, but it seems kind of absurd to me to think that all evolution took place on our planet in the life of our planet. Like it seems more probable that most of the evolution that had to have taken place for all of this stuff to be here, all of this life to be here, that it would have used the entire lifetime of the universe.
Yeah. Yeah, I agree with that.
Yeah, we just have evidence of the evolution that's actually happened on
Right.
Earth so far. Just
Yeah.
as far as fossil records, that's it.
Yeah.
But I see what you're saying, yeah, that there's other evolution that could be going on.
Like the very beginning is the hardest part to explain, right?
Yeah.
The spontaneous combination of all these protein and everything to come up with something that's actually alive is the hardest. I mean that
Yeah, where's the missing link that goes
Yeah.
from
dead
blob
stuff.
of stuff to living blob of
Right.
stuff?
Yeah.
But I also thought like there were issues with the timeline. They're like, well, you can look at like this one species and then look at another one, and like the time that it might take for one thing to become another is so great that they keep extending the idea of the
Yeah.
lifetime of the Earth.
Well, and they've reached like the limit of that now of 4 billion years, which is like if you go farther back than that, then you start to reach like points where our sun wasn't more than a protostar.
Yeah.
And they've got evidence of life, of like single-celled, like simple life being on Earth less than 500 million years after it supposedly formed. So there's almost no time for it to accidentally become. It had to have come here from somewhere else.
Right. That's kind of what my point is that, and I don't really know where this is going. It's not like I've worked it all out and figured it all out. It was just, this is.
Come on, Kyle.
I'm just doing the easy part, which is just like, yeah, that's bullshit.
Yeah.
But yeah, it just seems, in one way of thinking, more probable that advanced forms of life could have developed in other places in the universe that had more time, or
Right, because you have, 14 billion, what is the estimated age of the universe post-Dark Age?
Give or take a few,
Yeah.
few hundred million.
A few hundred million. Yeah, it's not quite accurate. So, I think on the last podcast, we were talking about this, about the difference between the evolving Big Bang universe and the steady state theory that was popular before that. Mm-hmm. What do you think about that and the idea of constants? Like I have this like pet peeve, or not really a pet peeve, but this issue with the idea of constants, which were from the steady state theory being dragged into the evolving universe theory of the Big Bang, and sort of maintained here by like they're pretending that like, oh, all these constants sprang into being in the few nanoseconds after the Big Bang, and they've been constant ever since. And yet the entire rest of the universe is constantly evolving and changing. And
Well, so let's start with constants first. So say you take the speed of light.
yeah,
It's been shown experimentally that the speed of light actually does change slightly.
Yeah. We talk about that with refraction.
It's not a constant. Now, if you take our measurements and average them, we get a pretty good idea of a constant.
Right.
But
that's over the past, 100 years?
Something like that.
Right.
But we don't know if, that's fluctuating because of the location of the planet in the solar system or the location of the solar system in the galaxy.
The location of the galaxy in the cluster.
Or if it has anything to do with location anyways.
Right.
But it's startling to me the reluctance they have to actually look at that. Like the scientific community has to actually look at that and admit that it's not a constant. It fluctuates.
I mean, because the E equals MC squared is based on the idea that it's a constant.
Yeah.
And if that fluctuates even in tiny amounts, that's going to drastically change the rest of that equation.
Because you're squaring the speed of light.
That's right. It's fucking squared, which makes everything else in there change a lot if it changes a little. Yeah.
So I think, steady state just doesn't make any sense.
Right. No, I completely agree with that. Well, I mean, also think about the decay rate of, for the constant of decay for radioactive particles. That's also a constant. Yeah, and we use it to date everything.
Which is another, approximation.
So if it isn't constant, if it's been changing over the lifetime of the universe, then for us to extrapolate that what we think is a constant into the past could result in humongous errors.
Oh yeah. It's like what you had brought it up in a previous episode about the carbon dating.
Yeah,
and how if we have certain periods where we're getting a lot of particles bombarding the Earth, and then certain periods where we're not, but we're averaging out over the whole time span. That's not gonna work.
Yeah, it doesn't work.
Yeah.
So I don't know a whole lot about advanced mathematics. Never really got into it, but I'm curious, why is there the necessity to have this constant in these equations? It's like, from what I understand, it's always like, oh, you can take this thing and then you put some constant in there and then you can figure this out.
Like it makes the math work.
Yeah. If you have a constant, it kind of like anchors one part of it so you can sort of move everything else around it.
Okay. So if that one anchor
ceases to be anchored.
Yeah. But you don't know it and you're using it as an anchor anyway.
And that results in massive errors. Or if you have an equation that has no anchor, then it's hard to. You can shuffle everything around, but you never can really come to it.
So then the speed of light being a constant being used to figure out something like designing a rocket is useful right now because that speed could be considered a constant right now.
Right.
At least close enough for us to get the rocket right and be able to do what we need to do.
Yeah, so we have the current value. And that makes it so that when we do stuff that's happening right now, it's fine. Yeah.
Right.
But if we're trying to extrapolate it into the past of the future, that's where the errors come in.
Or when you start, say, wanting to move a spaceship at near the speed of light.
Right.
Or something like that.
Yeah.
But, when you're just going 18,000 miles an hour around the planet,
it's not
good enough for government work. The approximations work enough. So.
Yeah.
It gets the man into space.
So that's probably another reason why they're not too bothered by it. I'm sure all these physicists worry about it all the time.
That's just one of the many physical skeletons in the closet.
Right.
Yeah.
Well, like the fine structure constant that Feynman says they always worry about, 137. He says that they print that number out real big and they stick it up on the wall and they freaking worry about it. I still haven't been able to figure out why, but I want to print a big 137 in my room and just put it up on the wall
and try to worry about that.
And just look at it and be like, why are they worrying about that?
Physicist's worst nightmare. He walks in and the number says 138.
Oh shit! Okay, so. Another thing I wanted to bring up is and we've talked about this a lot, this engine they're building in NASA Skunk Works.
Yeah.
the so-called reactionless drive.
You talking about the copper pyramid with the
The copper cone.
microwave in it?
Yeah.
Yeah. So basically, as far as I know from the story, like a British guy, right? It was a British guy who initially announced it. He was like, "Yeah, so I built this thing, and it's just a copper cone, or like he said, a pyramid, and the wide end is open, and they have these microwave antennas facing down into the inside of the cone or the pyramid, and when they shoot microwaves down there with these directional antennas, it results in thrust. Now it's a tiny amount,
Yeah.
but it's measurable. And so he announced this. He's like, "Yeah, so this is happening," and everyone was like, whatever, bullshit or whatever. And then like 4 years later, the Chinese just out of nowhere announced that they had built one, and they had shown thrust on it too. So NASA's like, "Well, shit, maybe we should try this.
Maybe we should look into this.
Maybe we should look into this." So they built one, and like the guys at the Skunk Works there. And did the same thing. They built it, and they were like, "Yeah, so it shows thrust." And then all these scriptards show up because this is America. They all showed up, and they're like, "No, it's just what they say it was first convection." They're like, "It's convection."
Thermal convection or
Thermal
something.
convection. So they put it into a vacuum chamber, and they tried it again. They still got thrust, and they're like, "Oh, it's interacting with the Earth's magnetic field." So they put it.
Faraday
They put the
cage.
vacuum chamber in a Faraday cage, and they did it again, and this is most recently. They still have thrust. So now we're just waiting for the next excuse that the scriptards have for.
That's what the scriptards have printed on their wall, and they're worrying about it.
Thrust? Question mark.
Yeah, because it seems like they claim that it seems to violate the conservation of matter and energy, right? It seems to violate the conservation of something, momentum.
Yeah, right. Because you have to have something to push off of, and then one thing's going to go the other way. Like, we don't worry about the rocket fuel out of the back.
Right.
We're like, well, where did that go? And how fast was it moving? We're just paying attention to the rocket and like, yes, it's going the right direction.
Right.
We're getting
Well, it's
thrust.
kind of like we're not paying attention to all the rubber that comes off our tires on the road.
Yeah, exactly.
Yeah.
I was trying to figure out.
Where is all that rubber?
I was trying to figure out if the atoms in the tire are not actually touching the atoms in the road.
Oh, yeah.
How are pieces of the tire coming off onto the road?
And then why don't we have giant piles of rubber on the side
Yeah.
of the road?
Yeah.
Exactly. Nope, the road wears down and the tires wear down, and nobody knows.
I think
It goes to the land of drier sites.
I think because of the way
the conservation of tire rubber.
I think because of the way that because actually it's a really tiny piece of your tire that's interacting with the road, so a lot of it probably turns into gas.
yeah,
Which is mostly
it evaporates.
Right, it evaporates, but it evaporates into what? Like carbon and other stuff.
Right.
And the grass on the side of the road eats it, which is why all the fucking deer sit on the side of the roads, because that's the best grass. Because it gets all the carbon from the exhaust and the tires. That's my theory. Because I've been trying to figure out why the fucking deer always sleep on the side of the roads. Like, you have all this like forest
land.
open land where nothing kills you, and you're sleeping on the side of the road.
Yeah. So the state of Texas tried to screw over the deer by planting KR blue stem on all the sides of the road because they were like, "This grass is worthless," and then all the deer were like, "How?" Nom, 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 nom.
That's right.
They all thought it was like worthless agriculturally. And, man, the deer just
The deer love it. Yeah. Even if they don't eat it, it makes great beds.
Yeah,
Yeah.
that's true.
Yeah.
Damn it. Gravel. Put gravel back there.
Yeah. Yeah. So if this reactionless drive is true, I should be able to like fly to space by picking up my freaking shoestrings, right? Just like lift myself up on my shoestrings. That's what the scriptards are saying.
Yeah,
It's
that's what
but they say
yeah.
it's the bootstrap method, right?
Yeah.
Like lifting yourself with your own bootstraps.
Yeah.
Like they're like, it shouldn't work, conservation of momentum or whatever. So what could be happening? Do you have any ideas?
I really don't. I haven't read into it since I think maybe a year ago when they did the last update.
I was trying to look at it through the elastic universe concept. Like maybe it's doing something where it's reverberating with the ether.
Yeah, I don't
And
know.
that's what it's pushing off of.
I haven't looked into it enough to know or to even try to figure that out.
Well, so let's think about it. We've got microwaves entering a cone
Of copper, yeah.
of copper, which is basically
A mirror
a reflector, and waves have energy.
Yeah.
So you're basically, it's like a headlight cone reflector where you're focusing light in and then it's being focused and pushed back out.
Right.
But
But they're saying that there's
where's
not
the multiplier coming from?
There's a multiplier in there somewhere
Yeah.
because those microwaves don't have enough mass to.
Now maybe it has something. Maybe there's a constructive resonance.
Yeah, that's what I was thinking too.
That's amplifying
Yeah.
microwaves.
And maybe,
But it seems like that should be detectable. Like, if it's
Yeah, you'd
coming
think
back,
you'd be able to
if it's
see,
coming
like,
back out amplified, it
harmonics.
should be burning stuff behind it or whatever. Like, even
Well, but if it's microwave, that there's not a chocolate candy bar in your pocket standing behind it.
right. That's the question. Will it cook popcorn?
Will it cook popcorn? So you're saying I can fly to space and cook popcorn at the same time?
Man.
I remembered what my question was.
All right.
And we still have like 11 minutes.
Wait.
11.
11.
So it wasn't really a question. I just wanted to talk about conductors and insulators.
Okay.
In terms in terms of electricity, but also like it seems that they work the same way in terms of heat. Or some of them do and some of them don't. But like the physical properties of the things that are conductors and why they might be conductors and why they might be insulators. So, thinking about glass, like it's a great insulator for electricity, but it's also a really good heat insulator. Like you heat one part of a glass and it doesn't want to spread that heat
transfer.
throughout.
Yeah.
Right. Whereas with a good conductor, you
heat
you
will
put a
spread
flame
fast.
to one side of a piece
It's
of
gonna-
copper, the
yeah.
other side's just getting hot.
Yeah.
It transfers all of that heat energy throughout the thing.
Which interestingly makes that one spot harder to heat because you have to heat the whole plate.
Right.
Yeah.
Exactly. So that's the way I've been sort of looking at conductors and insulators and what, just trying to understand them better or just think about them in different ways.
Yeah. So, looking at something like glass, the way I understand it is, with something like you have glass, which is silicate.
Right.
So, it has a crystal structure, and it's got a rigid atomic structure that it conforms to. I think really what the main separating factor there between insulators and conductors is that conductors have free electrons
Right,
that
free,
can
yeah.
move between individual atoms,
Okay.
and whereas with a insulator, the electrons do not want to move around.
They're all bound up in there.
They're bound in the structure. Yeah.
Yeah.
That's interesting.
So how does that result in also the same situation with heat? Like the heat is exchangeable in the conductor.
Because heat and atoms is represented by electrons jumping shells, right? Isn't that?
Yeah, that's the energy level. Yeah.
Yeah.
Which is the vibration of the
which is
thing,
the
which is the
vib-
heat,
yeah.
basically.
Yeah.
Yeah. And then there's, along with that, I've talked to you about this before, but there's this, a scale, basically. I think they call it the triboelectric series.
Yeah, that's right.
Where if you have a group of materials, you can put them in a certain
In an
order,
order,
which has
yeah.
to do with ones that want to shed electrons, ones that are more willing to like take on electrons, and you can put them in order in that way. And so the two materials that are the furthest apart from each other in the list
good
are
conductor
going
and insulator,
right,
yeah.
but they're also going to create static to when you put them together or
And
rub them together.
Yeah, because one will
Try to
want
shed a whole bunch, and the
shed
other
a
one
bunch,
won't want to take them.
it. Yeah.
So they'll. How do they know they don't want this?
I don't want those. And then isn't there something about it when the material won't take electrons, they sit there as a field on the outside of it?
They like collect around it because like one material will be shedding them because it's
Right.
when
It's
it comes
easy to
it
strip
doesn't
them off,
It's
yeah.
like they're
It doesn't
assholes.
care if the other one doesn't want
That's
it,
right.
yeah.
They're assholes. They don't care that the other material doesn't want them.
it,
They're just
yeah.
like, here you go,
they
man.
just want to get rid of it. Yeah.
Right.
Yeah.
Yeah.
And all it needs is that contact, so you can take the fur coat or whatever and the glass ball and sit there and rub the fur on the glass ball.
See the fur start to stick to glass
But
ball.
the fur is like giving electrons over to the glass ball, and the electrons are like trying to. Glass ball's just like nope.
And they're trying to get as far away from each other on the surface of the ball too.
Yeah.
So they're not gonna like want to sit next to each other. They're gonna go to the
Yeah.
opposite ends of the ball, and then so as you add more and more, they're gonna still be uniformly distributed around it. The charge will still be uniformly distributed around it.
Yeah.
Yeah, so you walk up barefoot and you're like, oh, that's a pretty glass ball.
And you
And they
just
just-
sunk it all back.
Yeah, they all just like jam into the end of your finger, and the electrons in your toes are like, oh, they get shoved out of it.
I looked at one of the
So
old.
that's the basic idea,
Yeah,
right?
yeah.
Okay.
I looked at one of the old machines that they used for charging Leyden jars. This is an old version.
like a Van de Graaff generator.
Like
kind of
well,
thing?
they were the old. Well, it was a glass ball, and they had a big like
a belt running.
yeah.
past
Well, you
it.
could the one I saw, the glass ball was connected. It had a handle connected so that you could rotate it, and then somebody would wear silk gloves, and then just put their hands on the bottom of the glass ball with those because the silk and glass is like he was saying the fur. And you
Yeah.
put your hands on the bottom of it, and then there was a chain that was dangling, touching the top of the glass ball, and that chain was connected to a wire that went over into the middle of the Leyden jar. So you would charge it like that. The silk gloves would create static on the glass ball, which would be carried by the chain to the wire to the middle of the jar while somebody was spinning the freaking handle.
Badass.
It's pretty cool.
Static generator.
Yeah. I would love
cool.
to build one of those.
So how do we turn the Earth
Yeah.
into?
We just need to stop some massive silk gloves.
Yeah, so probably the solar wind works that way.
On that big
Yeah.
red band
That's
that
why we
goes
get the
around the
aura.
equator.
Yeah.
Wow. Whoa.
Wait, what? I was making a stupid joke. I missed what you were
If the
saying.
Earth is the glass ball, the solar wind is the silk gloves, and that's what gives us the aura, the aurora borealis. Now we just need a giant chain.
Well, we tried that.
Oh yeah, they tried that.
Oh, that
Fried
was
the
the tether. It was the tether.
STS-80.
Of course. Full circle. Damn it.
They should have put the Leyden jar on Mars.
That's right.
Yeah.
The Leyden jar was the shuttle, which
Yeah.
is a bad idea.
So now I'm gonna ask you to speculate, but what do you think about? And I don't know how much you've looked into this, but the idea that ancient civilizations here had and used electricity for power, or like that they had that knowledge and capability.
I think it's very possible. I mean, everyone knows what the fuck lightning is.
That's true.
Yeah,
Everybody's experienced it. at least,
Everyone's
yeah.
experienced lightning.
And static shocks.
Yeah.
I was thinking about that the
Yeah.
other day. Like everyone, no matter what, has been shocked by
Shocked.
something
Static.
with static electricity.
Yeah.
right.
And like if you were
Not back when they were wearing butt flaps. No, they weren't
You
getting
know,
static shocks from wearing butt flaps. They were
Those fur-lined butt flaps sure didn't create static on anything. Huh?
no way. No. And when they were carrying around, they were carrying around obsidian arrowheads and stuff. No.
Yeah, no.
They never.
Not once.
No.
Not once
Yeah,
ever.
no.
And then, of course, the royals, the leaders did, because they wore like big amber.
Oh yeah.
It was
It's
some
like
big
rubbing on
yeah.
cloth all day. Yeah.
The wrath of the king.
Yeah. Yeah, I think it's entirely probable. I was talking to someone the other day about it. It just seems to me like our modern civilization is so short term compared to the time we think the Earth has been here.
Yeah.
And looking
even
at
just
the
time-
age of stuff we found,
Yeah.
it doesn't make sense that
And even just time of how
we're the most advanced that has been here.
even
Yeah.
just time of how long we think that humans have been, like anatomically modern humans that were technically as smart as we are, have the same brain capabilities with 200,000 years, and like recorded history goes back what, 6?
Yeah.
12 now.
12.
Göbekli Tepe.
Oh yeah. Well,
Fucking threw them for a loop, didn't it?
yeah, but there's
Bunch of skirp derps getting their asses handed to them.
But that's what's fascinating about Göbekli Tepe is the giant gap between 6,000 years ago and to it.
Yeah. The 6,000 years between.
In between,
Yeah.
Which is just indicative of the giant error in the standard model.
Yeah.
Yeah. Error.
Error.
Yeah, I think this, the standard model relies on the fact that we are the most advanced civilization that has been here ever,
And linear development too.
and linear progression.
Yeah,
and
Uniformitarianism.
and if we don't know how to cut and move those big ass blocks,
Yep.
we can't do it.
Yep.
The only cranes that could do it
Or skyhooks.
would require too many cranes around the block to go anywhere.
Right. We were talking about
My dad brought this up the other day, that the other thing that I had not heard him say this before, but the other thing that is required when moving very heavy loads with cranes is level ground.
yeah.
Yeah.
You have to have a massive, very stable,
Flat,
level
level
structure
ground,
Right.
on the ground for the crane to be on.
Yeah.
Peru.
Peru.
Yeah.
Yeah.
Right. They use
Mountains. It's nothing but mountains, and like all that shit in the Andes, and they're moving those huge blocks, kilometers up
Yeah.
and kilometers down.
So let's say now some cataclysm happens or whatever, or we're wiped out. Modern civilization is wiped out. These massive, the massive electrical grid that we have in these stations that have all these vats of oil, with all the stuff you were talking about. How long is that going to last? How long is that going to be there to be found by future
buried,
humans?
If they're buried a lot longer than if they're in the open.
Yeah.
But
in
they're
the
all
open.
made out of the metals will corrode and oxidize and
Yeah. So if they're out in the open, I mean, 200-300 years, stuff's
Yeah.
gonna be gone.
right. That's what I'm thinking.
And
So,
even if it's buried 10,000 years from now, it'll be unrecognizable. It'll
Yeah.
be a mush.
Yeah.
It'll be a mush of crap.
yeah, and especially if an ocean comes around,
Oh, yeah.
and then goes away, it's like goodbye.
Yeah.
Yeah.
It's gone.
I found a fishing rod holder in the ocean that was made of rebar, but I didn't know what it was. I pulled it out, and it was just this huge, fat, like as big around as a baseball bat glob of shells and weird. I was like, "What is this?" And I took it home, and it was just like this really cool looking thing. And we stuck it in our little garden or whatever, and it slowly began to shed the rusted.
Yeah.
And finally, when it fell apart, I could see the fishing rod holder, and it was this tiny little thin wire of rebar. It's like
That was still left.
all the shells and everything had fallen off of it.
And it was probably lost like 3 months before you
right,
found it.
exactly.
Yeah. Yeah, no, it's so easy for the earth to wipe the slate clean.
Yeah.
It's the earth itself is a terraforming machine.
Right. It's constantly
It's constantly changing.
rolling the surface over.
Yeah.
It's just that the reason why I brought that up is because Scriptards, again,
Yeah, Scriptards.
their argument is like, well, why haven't we found, if they had...
Show me the potsherds.
If they had any of this technology and all this kind of stuff, then why haven't we found it? And
Because
it
it's been destroyed.
Yeah, it's like we make things out of metal, and that is what we use for the electrical stuff that we have.
Yeah.
And it's
Yeah.
It just
not
doesn't last.
permanent. It's not a block of granite.
Right. Exactly. I had this analogy I used to use where I'd say, so let's say that I work with a backhoe, and it's this gigantic thing made of iron. It's like almost indestructible.
Yeah.
Right. And I have a smartphone, and one day when I go to work, I want to show my coworkers, I want to show them this like stone hammer that we found. Right. So I bring this artifact from ancient times, and then I forget the stone hammer and my cell phone next to the backhoe, and we go home, and then everyone dies that day from some plague. Right. So I never return. In like less than a week, the cell phone's going to be worthless. It'll be completely worthless.
Yeah.
Like the battery will die, and then it'll start to corrode immediately or whatever. It may take a couple of 100 years, but the backhoe will be a pile of rust.
Yeah.
And like weird trace metals and oils and
Yeah.
shit like that. In 1,000 years, you won't be able to find the cell phone with forensics.
No.
You could tell that the backhoe was there with forensics if you knew what you were looking for. In 10,000 years, you won't be able to find the backhoe with forensics, but that stone hammer will still
be
fucking
sitting
be there.
That's badass. I mean, that sucks, but it's cool.
Yeah,
it's
no,
a good-
the indicators of modern civilization are not permanent.
Yeah.
They're very far from permanent because we've realized how much effort it takes to make stuff that lasts that long.
Right.
And it's not worth it in our society to do something.
To me, the biggest indicators of modern civilization are going to be the earth moving we've done. We've moved a lot of earth and making the freeway systems, and so if parts of that don't get completely inundated by tidal waves or whatever, there will be cuts through mountains.
Yeah, there'll be V's.
Yeah.
Gorgeous cut through mountains.
I still think that I see some of those from ancient times. Like sometimes you see this V and we didn't cut it, and I'm like, bam, proof of ancient civilizations, because it's like it just seems to me like that's what we're gonna leave too, is cuts through mountains and shit.
Yeah, they'll have evidence that we did it,
and no one will believe it.
There'll be drill holes there, right?
Yeah, there'll be drill. Yeah,
where they stuck the dynamite in.
That's right. The explosive gels. Yeah.
Yeah.
All right, I think that's it. That's it for episode 5th Town.
Well, thank you, GMA.
Yeah, GMA.
guys.
Great,
Awesome.
Great guest.
Yeah.
Yep.
I didn't understand anything you told us.
Yeah.
But it was great.
Maybe somebody will,
Maybe someone will.
and they'll find it before the next cataclysm, and we don't have to carve this stuff on stone.
Yeah,
I like your shirt too.
Yeah.
Thank you.
I like pig butts, and I cannot lie.
Like big butts. That
Snake
stone
snacks.
hammer will still be there.
That's right. Stonehammer will still be there. Snake next.
Next.
And you guys can contact us at brothersoftheserpent@gmail.com. You can go to the blog and put some comments there. That would be great. At brothersoftheserpent.blogspot.com. Thanks to Laura for the intros. Thanks to GMA for being a great guest. Thanks to Smith Sonic Studios, AWACS Productions, Aethrim Studios. Good night, Adamu. Get back to work.